Hello guys, so today we're going to look at this example 5b4 and I'm going to use this example to demonstrate how to use the steps we learned in class to solve any work energy equations for a rigid body. So here we have this homogeneous rectangular plate. So what that means is the mass is uniformly distributed. And so we know this rectangular plate it's released from rest, that would be a keyword with its upper surface being horizontal. So what we're looking at here, this is a position one. We assume the plane at O to be smooth. Right? We need to determine the maximum angular velocity of the plate as it rotates about its planed support at point O. So as we know, if we release this rectangular plate, this rectangular plate can rotate about point O and backward force. So there's one point we're gonna see a maximum angular velocity. And that also tells you at one point we have maximum kinetic energy. So this is a work energy equation. At position one, we have potential energy. At the position one, which is this maximum angular velocity position, we're gonna see maximum kinetic energy since all the potential energy being converted to um, kinetic energy. So now let's take a look how to solve this problem. We're gonna start with step one, two. Step one, step two. That's to draw a free body diagram. So at position one, so this is a position one, our free body diagram gonna look like this. The weight force pass through the mass center, let's call that point G, and point O is the support, so we have reaction forces Rx and Ry. And we can set up a coordinate system. Let's use INJ as our coordinate system. So this would be our step one, two. And step three, we look at all the forces in vector form. So we have one, two, three different forces. The first force, weight force, going to be negative mg on j. Rx equals Rxi. Ry equals Ryj. So that's all the forces in vector form. And step number four, we're going to write all the acceleration at mass center in vector form. So Ag going to have two components, Agxi plus Agyj. Okay, so that's the first four step. Should be pretty easy. Let's move on to step five. That's when you need to use Newton's equation. Sum of all your forces equals mAg. Now let's plug in all our force components. Weight force plus Rx plus Ry equals mAg. We can plug in all the INJs. Agx plus Magyj. So from this Newton's equation, we can obtain two scalar equations. One on I direction, we have Rx equals Magx. That's our first scalar equation. Second scalar equation is Ry minus Mg equals Magy. That's our second scalar equation. Okay, that's step five. From step five, we obtain two scalar equations. Step six is to apply Wheeler's second law, sum of all your moments. And here we have to pick a special case. We mentioned three different special cases from the previous video and lecture, and you can pick one of the special cases to simplify your equation. So here I would pick the mass center G. So my Euler's equation gonna be sum of your moment about point G equals Ig alpha. Now let's look at all the forces can cause movement about point G. Look at your free body diagram. So the only forces can cause movement about point G is Rx and Ry. This weight force passed through point G, so no moments from this weight force. So Ry gonna cause a moment about point G. It's gonna be counterclockwise, and the distance from Ry to G will be half of this length. So the first moment, positive, because counterclockwise, Ry times 1.5d divided by 2. That's half of that length. The second force, Rx, going to cause a moment about point G. The distance from Rx to G, the perpendicular distance is half the length of this edge, which is half of d. And that rotation, that moment is negative. So we have negative Rx d over 2. Those are the moments equal to Ig. Yeah, if you want to add directions, those moments should be on k direction. Ig, if you look up the table in page 303, Ig equals 1 over 12 mass times the width square plus the length square. In this case, going to be d square plus 1.5d square times alpha k. So this is our Euler's equation. And we can get a scalar equation on k direction, which is Ry 1.5d divided by 2 minus Rx d over 2 equals 1 over 12 mass d squared plus 1.5d squared alpha. This is going to be our third scalar equation. So far from step 1 to step 6, you can obtain 3 scalar equations.